The hypothesis tests about the linear model can be based on two procedures. We can make f-tests about regression coefficients or likelihood ratio tests for all parameters of the model. So likelihood ratio tests can be done also for the parameters of the random part of the model. So as I said, those f-tests can be used only for regression coefficient beta. And if beta estimates of regression coefficients are based on the generalized t-squares with estimated matrix V, then the test is called conditional f-test or walled f-test in literature. Sometimes we have a situation where this f-test cannot be conducted, and in that situation we could use so-called walled chi-square test instead. And these likelihood ratio tests as I said, they allow tests for all parameters, but they are not recommended to be used for tests about regression coefficients beta. The reason for that is that in some situations, they are badly anti-conservative, so they give very low p-values, even though there are no true effects. So let's take a closer look at this conditional f-test for regression coefficients. So we define the following two residual sums of scores for the constrained or restricted model and the full model. First, we define the residual sum of scores for the constrained model, and it is just a weighted residual sum of scores based on the assumed known variance covariance matrix V. And correspondingly, we define the residual sum of scores for the full model by using the model matrix and GLS estimates of the regression coefficients of the full model. And the test statistic is obtained by taking the difference between the residual sum of scores for the constraint model and that of the full model. So we see that difference necessarily has to be positive because the constraint model is a special case of the full model. Therefore, the residual sum of scores for the constraint model is necessarily higher than for the full model. So this is positive. The numerator is positive, and also the denominator is positive because it's the residual sum of scores, which is positive, divided by a positive number. So we get some positive number, which is called f-obs, observed f-statistic. And in this test statistic, p is the number of predictors in the full model, n is the number of observations in the whole data, and r is the number of restrictions, so how many rows we have in L matrix, or how many restrictions may be made to the parameter vector beta of the full model to obtain the restricted model. So we can equivalently define the f-obs as using this formula here. Sorry, I'm missing the denominator r here. The benefit of this formulation is that this does not require estimation of the restricted model at all, but we can base it only on the beta coefficients of the full model and the residual standard error of the full model. And if the null model is true, and if the data are normally distributed, or just the number of observations is high, then this f-obs follows f distribution with r and n minus t degrees of freedom. So this means that if we believe that the null model is true, and if we get some value of f-obs, and if that value is high compared to this theoretical distribution, then it is evidence against the null model. And if If the f-ops is very high compared to that distribution, then we reject the null hypothesis. So we can have, for example, this kind of situation. This is the f density of the f distribution with r and n minus p degrees of freedom. Now we have summarized our data in one single number. So there is one statistic computed using our data, and it is this value of f-ops. If our f-ops happens to be, for example, here, if this is our f-ops, then we see that it is not very rare compared to this distribution here. So it could be the probability to have f-ops even higher than we observed is the value here, and the area under this tail is called the p-value. But if our f-ops happens to be very far in the tail, so that this p-value is very low, then we think that we either had a very bad or good, whichever you think, luck, because we got data that seems to be very rare or uncommon under the null hypothesis. So we either have the case where null hypothesis is true, but we got the data that is very seldom observed from this population, or the null hypothesis is not true in the population. And usually if the p-value is below a critical limit, which is normally 0.05, then we reject the null hypothesis, and we believe that the null hypothesis was not true, the null model was not true, and therefore we start to believe in the full model. But anyway, we were not able to show that the full model is true either. It is just describes the population better than the null model. So in practice, this P matrix is not known, and the test where it is replaced by the estimate of V based on restricted maximum likelihood is often used, and this test is called the conditional F test, or mild F test also in some textbooks. But as I already mentioned, all procedures for testing the beta are based on this kind of procedure, where you first specify some constraints to the full model, and they can be specified by those L matrix, and then we compute the test statistic, that is an F-test statistic. Actually, sometimes we can use also T-test statistics, but it is the same, it's just a different way to do the test. So F-test is more general, so if you know F-test, you don't necessarily need T-tests, or you might need them only for one-sided tests about regression coefficients, but they are very seldom used. But you just compute the f-ops using the L statistic, L matrix you have, and then compute the observed F statistics and compute the p-value from that. And if the p-value is below your critical value, which is quite often 0.05, then you reject the null hypothesis. And all tests about regression coefficients are based on the similar procedures. I mean, on this procedure. But as doing those tests manually is a lot of work with L matrices and so on, computer programs do some tests automatically. Sometimes I feel that this automatical conduction of tests is causing more confusion than benefit, but it is very important to recognize that they are not doing something different from what we presented here, but they are just doing a lot of tests or several tests in a certain, following a certain procedures, and it's important to understand what kind of procedures they are following. So the default method, for example, in R, if you use ANOVA function, is to do type 1 tests, which are based on the sequential sum of squares. In sequential tests or type 1 tests, we add terms into the model in the order they are given in the model equation. So in this case, it matters in which order you have the terms in the equation when you specify the model. And when we speak about terms here, it means that the categorical predictor is counted as one term, even though it may be parameterized using several coefficients. So this means that within the function is specifying the L matrix that can sometimes include, or whenever you have categorical predictors with more than one level, it includes more than one row, and therefore it is testing, making hypothesis testing for all categories simultaneously, setting the all fx to 0 simultaneously. So first we make a test where the restricted model includes only the first term of the model, which is not usually the intercept, and the alternative model includes also term 2, but it doesn't include the terms 3 and 4 and so on. So we conduct test on this model, and then this gives us the p-value for the term 2 of the model. And the second p-value and test is based on the null hypothesis, where terms 1 and 2 are included, and in the full model we also have term 3, and so on. So this is how we increase the model, but in that case the full model is always, it's not always the same, but the full model is the one that includes the additional term. In the type 3 tests, which is also called marginal sum of squares, we follow a different procedure. Again, each term refers to one predictor regardless of the number of categories in a categorical predictor. So the first test is based on null hypothesis where the first term is dropped from the model, but all other terms are kept, and the full model includes all terms that are included in the model. And the second test is based on null hypothesis where term 2 is dropped, so we keep all terms except for term 2, and the full model is again the model that uses all terms, and this way we drop every term in term, and then that is how we get the so-called ANOVA table for the model. And it's important to notice that the p-values from these two test procedures are very different because they are doing different tests, and they also have different interpretations, so you need to be very careful when you interpret the results, that you really understand what's happening. And still, these two procedures are not sufficient in many cases, so they do not necessarily do the test what you want to do, and therefore you really need to understand the testing procedures and probably do them also different way, and not just using these procedures that are automatically run by the computer software. So if you just run in R the command ANOVA and then give the model, as I have done here, you will get this test based on sequential sum of squares for the model. So for example, this p-value here specifies that if we have a model that includes only diameter and intercept, then the diameter is a significant predictor in the model. So there is some relationship in the time consumption and diameter. And if the machine is included in addition to diameter, then it is also significant, and so on. Here are the marginal or type 3 tests. So here we have a type is equal to m, and now the full model is the one that includes all the terms: diameter, machine, diameter squared, diameter and machine interaction, and diameter and diameter squared, machine and diameter squared interaction. And now you see that the results are very different. What we see from here is, for example, that the p-values for all other parameters are below 0.05 level, but now this diameter squared has a p-value that is quite high. It does not mean that we should drop the diameter from the model. It just tells that for machine 1, that is our default machine, the second order term is not necessarily needed. But we still have this also. So whenever we drop this diameter squared from the model, it still assumes that we have this machine diameter interaction. So it means that we have the second power for machines 2 and 3, but not for the default machine. And this text here explains in detail the interpretations for all rows of this hypothesis testing. I'm not explaining them in this video, but you can read them on your own. It's very important to understand these procedures if you are going to do some modeling with hypothesis testing, and it's a very common cause of confusion among people who are doing applied analysis or analysis with real data. So we might be interested to see whether we could drop completely the second order terms from the model. Such a test was not done by the test we did here, but we can do that by specifying appropriate contrast matrix L for a general test that would restrict all terms that include diameter squared to 0. So that then it means that we need to restrict this term to 0, and then this term and this term to 0. And that L matrix has been specified here, and in R you can specify the matrix, for example, using these comments, and then if you look ANOVA and then specify that L is equal to your L, it is doing the F test for this kind of linear combination. You see here that it's dropping the correct terms, and you get the p-value 0.036, which suggests that the second power of diameter should be included either at least in one of the machines. We can conduct the same test also using ANOVA with argument terms. So these terms directly we specify which terms of the model are dropped, and the numbers here refer to the rows in the output from ANOVA. So if you want to check which terms you drop, you first run the ANOVA and then check the order of the terms in the model, and then you select the terms you drop. And you see that we will get exactly the same result. It is the same test, just done in different way. We might also be willing to test whether the shapes of the two machines are similar. I'm not sure if that makes sense from technological point of view, but technically it's interesting. So it means that we would set beta 5 to beta 8 and beta 6 to beta 9. So it means that the first and second order terms for machines 2 and 3 would be equal. And this is implemented by specifying this L matrix here, and then by doing the hypothesis test here. And the p-value here is low, so it seems that the common curve for the shape of the curve could be similar for machines 2 and 3, and there might be only a level shift in the curves. And we could also make a test about the common curve for the two machines. So we could specify that beta 4 is also equal to beta 7, and this test gave a p-value of 0.028, so it shows that there is a level shift between those two machines. And we could also make a test whether all three machines differ only in terms of intercept, but such a test gave a p-value below 0.0001. The code is not shown, so it means that we really need the interactions between stump diameter and machine. And to conclude, the final restricted model, which assumes linear dependence for machine 1 and common first and second order terms for machines 2 and 3, is sufficient. And if we want to test those restrictions jointly, then we should formulate this null hypothesis and formulate the L matrix that includes 3 rows for this model. And the p-value from this kind of model test was quite high, so we are satisfied this kind of restricted model, and then the model is of this form. And here is one possibility how this kind of model can be specified. We also need to be more careful with the formulation of the systematic world. So here we especially specify that this variable gets value 1 or true whenever machine is not 1, and that's how we get these common terms for diameter and diameter squared for the second machine. We can discuss about this in the lectures if this is not clear to you. Then the second possible procedure was the likelihood ratio test. And the likelihood ratio is twice the difference between the logarithmic likelihood of the full model and the constraint model. And asymptotically, this likelihood ratio follows chi-square distribution with r degrees of freedom if the null hypothesis is true. But this is only asymptotical result, so that's why it's not that nice result as nice results as the f-test. But the good thing is, as I said, the number of restrictions is r, but we can also make restrictions to the variance covariance structure of the V matrix of the model. And let us look at the example. So we earlier fitted a model for processing time of stumps. So the mod 1 was the OLS model, mod 2 included non-constant error variance but no autocorrelation, and mod 3 included also constant error variance. If we want to check whether these models are really different, we have a very nice tool in R. We can have this kind of several argument form of the ANOVA, and now this ANOVA function is doing the likelihood ratio tests for the three models, and it's automatically noticing which one of them is a special case of the others. And what we now see, for example, from this the result, the rows 1 and 2 from this table, we see that the model 2, which was included the variance function, and model 1 didn't, the p-value that compares these two models is very low, which means that we reject the null hypothesis about constant error variance, and we select a model with variance function. Then the second model makes a test between models 2 and 3, and so it computes the likelihood ratio test, and it gets a p-value 0.004, which means that the model 3, or if model 2 were true, then it would be very unlikely to have such autocorrelation in the data that we observed. So it seems we reject the null hypothesis, and this justifies the choice of using both power type variance function and the modeling the autocorrelation of residuals using AR1 process. Okay, then we could also make t-tests, or we can have a situation where we are comparing non-nested models. So the cases where the two models are not special, that the null hypothesis is not making a restriction to the model specified by the full model, but we have two like alternative models. If you want to learn about those, please read the lecture notes. I just wanted in these lectures about hypothesis test to give a general idea, because the f-test for regression coefficients is the tool you need in 99% of the cases. Sometimes you may benefit from the likelihood ratio test for the variance covariance part. And then something that was mentioned shortly in the beginning of the video was that Wald f-test, which is sometimes needed when we have group datasets, but there is also example about that in the lecture notes.